let me continue now after the break. So there's one question in the chat. So the question is on dynamic code updating. So the question is, if one process can keep the old version of the code, is it possible that we can't make new updates because of one process never updating? So the idea is you have many processes running in the module, and we want to update, but one process never updates. It keeps running the old code. So yes, that would be a bug. So if one process for some reason does not update the code, then the module cannot be completely updated. So that's a bug. So it depends on the reason why the process is not updating. If the process is not updating because it has a bug in there, or maybe it's not updating because it's waiting for a message from another one, and the message is not arriving, and so it cannot update. It's not ready for updating. Actually, there is a way in Erlang to solve that problem, is you terminate that process. So the supervisor can actually notice that the process is not updating and can kill the process or restart it. So there's actually a way, if the updating is not happening because of a problem, an error somewhere that you cannot avoid, then the supervisor can actually force that process to die, and then you can update. So the question is actually a very interesting question, because there's actually ways in Erlang to force then the process, the module, to update. Okay? So it depends on the application, because you cannot get rid of bugs in general. Sometimes if a process is buggy, you have to terminate it. You have to kill it. This is the Erlang philosophy. So let me now go to the second part of the course and talk a little more about the Erlang philosophy of how to build robust software. So this is a very interesting philosophy. Let me go to the slide now. Okay, so Erlang provides some programming abstractions for building robust systems. So let me talk a little bit about the Erlang philosophy, because there's a lot of discussion around Erlang philosophy, and the Erlang programmers are very strong believers in this philosophy. So it's actually very interesting philosophy, and it's very important to understand how Erlang is thinking. So the question is, how can we make robust software that keeps running forever? And popular languages, for example, Java and Python, are completely inadequate. They do not provide the mechanism necessary. From an Erlang point of view, Java is extremely unreliable. Erlang programmer would hate writing thing in Java, because it's always crashing and he cannot do anything. So the question, how can we make robust software? So Erlang has built a system based on some principles. So these principles, I'm taking them from Joe Armstrong's PhD thesis. So Joe Armstrong is one of the main designers of Erlang. So he has written a lot, and he has written some very nice books on how to use Erlang. So the principles. First of all, first principle, you cannot eliminate errors. So people, when they write software, they try to reduce errors. Okay, you fix bugs. People fix bugs. But there will always be some bugs remaining. So the Erlang principle says you cannot reduce the errors to zero. There will always be some errors left. So even if you do really, really, really good effort to debug, there will be some errors left. So, and that's actually a true principle. It's what we observe. Even if you make your program very solid and you test and you debug, there will still be some errors left. Therefore, you have to handle them. Okay? You cannot assume that the software will not have errors. You will have to assume there will be errors. So you need mechanism to handle them. And we're talking about both hardware and software errors, not just software, any kind of error. Maybe the process crashed because of a hardware problem, or maybe it's a software problem. For Erlang, it's the same. We have to handle it. Okay? So the second principle then is the unit of failure, that we need strong isolation. So we divide our system into parts, into boxes, components, and when one of the boxes fails, the others do not fail. So it's a unit of failure. An error occurring in one component will not affect the others. So we have isolation. So we have separate boxes. This is very different from Java. In a Java program, the whole program is monolithic. It's one big box. If something fails, the whole thing fails. So in Erlang, we say, no, we don't build our software like this. We build it as separate boxes that are isolated. And if one box fails, the others do not fail. Okay? So we have this isolation, and boxes are units of failure. And now the third principle is fail fast. So when a program is doing something wrong, don't try to fix it inside. Just fail as quickly as you can. Fail fast. When there's a problem, don't try to fix it inside the process, but fail immediately. So either you are working correctly or you stop quickly. So fail fast. Fourth principle is that failure should be detectable. If one component fails, the others should see that. They get notified. This is actually what linking is doing, of course. And then the fifth principle is no shared state. So this is actually a consequence of the second principle, but message passing. So the components are talking through messages, but there are no shared state. There's no pointers going between them. There's no memory that is accessed by all components. They are not sharing any state. Okay? So these are the principles. So how does Erlang build on top of this? So we'll see now what Erlang does. So Erlang actually has a few slogans to help you understand how it's doing. The most famous slogan of Erlang is called "Let it crash." If you can't do your job, crash. So when a process is running, something is going wrong. Maybe it receives information of the wrong type, okay, from another process. It's not its fault. It's receiving something wrong. Or maybe it tries to open file, doesn't work, or something goes wrong. The Erlang philosophy says, don't try to fix it. Just crash. Okay? One simple state, crashed. So when a process cannot work, it just crashes. So that is the philosophy. All the possible failure states are mapped to one state, which is crashed. Okay? This makes things very simple. So then how do we fix it? Then it goes to another slogan, let someone else do error recovery. So if one process crashes, the problem will be fixed by another process. Okay? And the reason is that hardware and software errors can both happen, and trying to solve them inside the process is complicated. But we don't want to make the process complicated. Okay? The process crashes. So the problem will be solved by another process. Another process will detect that this one has crashed and will do something to fix the problem. Okay? So let it crash, and then someone else will solve the problem. And then the third principle, which is a very interesting one, is do not program defensively. Maybe you have heard of defensive programming, that a program should always check things. It should check the types of when it receives information. It should check the result when it does calls a function. Check, 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 check. Always be very, very defensive. So the Erlang philosophy is this is not useful. It's not productive. First of all, it makes the program complicated. And what do you do when a check fails? Do you try to fix it? Do you what? What do you do? And in any case, it will not remove all errors. The checks will not be completely solving the problem. There will still be errors. They will still occur, and they still need to be handled. So the best way is not to do defensive program. Keep your program simple, and if it goes wrong, crash. Okay? Map all errors to a single fault state, namely crashed. So no matter what happens, if something goes wrong, crash. Okay? So that's the Erlang principle. Processes, don't worry about process crashing. You have to encourage crashing. Crashing is good. Okay? Failure is good. Failure helps you. So in many systems, you try to avoid failure. Erlang systems do not try to avoid process failure. They say, we encourage processes to fail because we will fix the problem at another level. Okay? So that's the Erlang philosophy. It can seem very strange if you're not used to building robust software, but actually it works very well. And they designed it over many years, and you will see how it works. So in an Erlang system, so Erlang, the platform is called OTP. And OTP supports a number of a hierarchy. When I'm building a big system, there's different kind of system. Okay, so the main system is called a release. So a release is the full thing, is all the information necessary to build and run the complete system, including software archive and a set of procedures for installation, including upgrading. So this is the full deal. That's the biggest one. The second one, a little bit simpler, is called an application. A single application. So this would be like a web server or text processor or some big data tool, whatever, a database. It's not the entire system, but it's just one application. So very often a release consists of multiple applications that could be independent, or maybe there's a dependency, and maybe there's a database application, and then there's a web server application, and the web server uses the database. Those are two applications inside the release. So applications are also units in Erlang that can be managed. And then the next smaller step, and this is the one we're going to look at very closely, the next one is called behaviors. So this I mentioned already. So a behavior is a concurrency pattern. A behavior is a set of processes that together implement some kind of concurrency pattern. So, for example, there can be a generic server. Any client server, there's a client-server behavior. Or another one, a very important behavior, is called supervisor. A supervisor is a tree of processes. It's a hierarchy with one root and with sub-trees, and the children on the bottom are the workers doing the work. So the supervisor will monitor the behaviors, will monitor what's going on, the child behaviors, and it can stop them, it can terminate them, it can start them, it can restart them. So the supervisor is actually observing the system. And then the very lowest thing are the actual workers. So these are the actual processes that are implementing the behaviors. So gen server behavior, gen event behavior, or gen finite state machine behavior. Okay? So let me say a couple words about behaviors, and then I'll go to the chat. So behavior is a very important concept in Erlang. So what's the idea? Well, assume now you're writing a program. Okay? Some parts of the program are hard to write. Some parts are easy. Okay? The hard ones, you want them to be written by experts. Okay? It's clear. You don't want everybody to write very complicated stuff. The easy ones can be written by regular programmers. So the way to do it is to put all the hard stuff into a special place to make it generic. So that's the idea. So now let's look at concurrency and fault tolerance. So these are difficult. So concurrency already is difficult. In message passing, it's actually can be difficult. Fault tolerance, when things can crash, is even harder. So they are difficult. So how do we handle it? Well, we put the difficulty inside of behaviors. So a behavior is a generic component that hides the concurrency and the fault tolerance. The complicated bits are inside the behavior. So the programmer that uses the behavior only has to plug in simple things. Okay? So behaviors are very similar to programming patterns, but they're actually libraries. They're kind of like higher order libraries. You instantiate the library and you plug in what you need to do, and then the behavior provides the functionality. Okay? So that's the basic idea. You want to hide these things. Okay, let me go quickly to the chat. So, of course, OTP provides many, in fact, all of the really important ones you need for applications are in OTP, and it's explained in a lot of detail. You can look at system documentation of OTP from Ericsson. The latest version is from March 2020, and it's a huge document with many, many examples how to use these behaviors. So if you want to write concurrent fault-tolerant programs in Erlang, it's actually very easy by using behaviors. Okay, let me go quickly now to the chat. So you can see the idea. Let it crash philosophy. And then we will see how Erlang supports this. So there's a question. What is my point of view on defensive programming? Actually, I agree with the Erlang point of view. If your system supports it. So in Erlang, you don't do defensive programming, but instead you use supervisors and you do let it crash. Now, if you write Java programs, there's no supervisor, so you have to do some defensive programming. But defensive programming is a very weak idea. It's kind of a hack, okay? It's not a real good solution. Sometimes you have to do it if your system doesn't provide anything else. But if your system provides a better mechanism, then don't do defensive programming. So in Erlang, the supervisor mechanism using let it crash is actually a much better mechanism than defensive programming. Okay, so that's my answer for defensive programming. Sometimes you're forced to use it. If you're writing in Java, you have to do it because crashes in Java are very nasty. You don't want crashes. So you have to do some defensive programming, but it's kind of a hack because Java does not really support building robust software. This seems kind of strange to say that, but from the viewpoint of an Erlang programmer and who has extremely high reliability, systems that never go down, he looks at Java and he sees, how can I write a robust programming in Java? The system does not help me, okay? So Erlang has these mechanisms that are used instead of defensive programming. So try not to use it, but sometimes you're forced to, but try not. If you have a choice, don't use it and use a system that gives you better mechanisms, okay? So that's okay. So let me go now. I'm going to now start presenting more of the ideas, and then I'll show a little bit more in detail how the behaviors work. So let me go back to the slides now. So first of all, let me show you what are the standard behaviors in Erlang OTP. So there are 5 standard behaviors. And actually you will be somewhat familiar with some of them, you'll see. So there's the generic server behavior. This allows you to build client servers, robust, fault-tolerant client servers very easily. It has registration built in, starting, stopping of the server, timeouts, managing the state, synchronous or asynchronous calls, error handling. It's all handled in the generic server, and the whole thing is concurrent and fault-tolerant. Very easy. So that's the generic server. The second one is the generic event handler. So events happen very often in concurrent systems. You can have, for example, events coming from outside. Pressing a key in a text editor can be an event, but you can also have events in a database. You need to log the events sometimes, keep them on a permanent storage. So you need to send notifications to parts of the system that are waiting for events. So event is kind of important information traveling around the system, and you have to collect it and notify the right people. So there's a generic event handler. And then the third one is one that we have seen in this course, is the generic finite state machine. So this one is actually very nice. Remember the lift control system where we had state machines, where we have to, how do you define a message passing application? You have to define these state machines. Well, the generic finite state machine is helping you for that. It does all of the low-level stuff for that. So applications are modeled as finite state machines. So we have seen how that works. So Erlang gives you strong support for that. So this is very similar to what we saw. An application is in a state, it receives an event, and it transitions to another state, and it does some actions. So this is actually very similar to the state diagram we have seen. It's actually exactly the same. Okay, so that's the generic finite state machine. So this one will often be the heart of an application. Okay, you will have a couple of finite state machines, the lifts, the floors, the controllers talking to each other. You see? So Erlang supports that very nicely. The fourth one is application. So an application is an important unit. It gives you a whole bunch of packaged functionality. You can start it and stop it all together, and you can reuse it in other systems. For example, a database could be an application. Maybe you need it in a web server. Maybe you need it in some other kind of application. So Erlang provides support for treating that as a box, as a unit. And then the fifth one is a very important one, which I have mentioned a few times, which is the supervisor. So the supervisor is the generic toolkit for implementing the supervisor hierarchies, which are the basic mechanism for making applications robust, where whenever you're running, someone is looking at you, which is the supervisor. Okay, and the supervisor sees if you have a problem, the supervisor can restart you or can observe whether something is going wrong. So all Erlang systems don't run by themselves. They're always being supervised. There's always someone looking at them, observing them to see whether everything is going fine and fixing a problem if there's a problem. Okay? So this is the basic mechanism for Erlang that you use instead of defensive programming. Yeah? You will always use the supervisors. And it's very interesting. Supervisors are automatically part of all these other behaviors. All these other behaviors are designed to work in a supervised fashion. You have to do almost no effort. This is built in to Erlang. Okay? So these behaviors will hide most of the complexity of each of these concepts. Finite state machine, server, event handler. Concurrency, fault tolerance are extremely simple using behaviors. And all the non-supervisor behaviors, these four first ones, are designed to be pluggable directly into a supervisor hierarchy. So everything that runs in Erlang can be supervised. Okay? So the supervising concept is very important. Okay, now there's a couple, before we explain exactly how it works. So I'm going to explain the server and I'm going to explain the supervisor. So you see how these things work. I'm going to explain two other things provided by Erlang first. One is the stable storage. So it's clear, when a supervisor sees there's a problem and it has to restart the process has to restart in a consistent state. So you need a kind of database, a stable storage. So the stable storage is the friend of the supervisors. So the supervisor and the stable storage are working together. Okay, so the stable storage is an important part of the Erlang's resilience. So it's actually what the supervisor uses to restart the system. So Erlang provides 3 levels of stable storage, which are more and more flexible, but also more and more time-consuming. So the simplest one is called Erlang term storage. This is in-memory storage. And so this one has limited size and concurrency ability, but it's extremely fast. So this one is what you use when a process fails, but the node does not fail. A process fails inside the node, you can use ETS to restart that process with consistent data. So this is extremely efficient. Okay. Then there is disk-based ETS. Same ability as ETS, but stored on a disk. So this is if the node itself fails, then you have to go to disk, the stable storage. Okay, so both of these are limited to single nodes. And then finally, you have a full-blown transactional database. It's built on top of ETS and DETS. This is much more expressive. This is called Mnesia. So Mnesia is a full-fledged like SQL relational transactional database supporting distribution and replication on multiple nodes. So this, for very complex applications where you have to store complicated information, you want to use Mnesia. So you have these different levels. You start with ETS and you can go further if you need the expressiveness. But ETS is extremely efficient. It's blazingly fast, as they say. So that's the stable storage. And a final point is testing. So what we've seen up to now is designing for resilience. We've seen the fact of using behaviors and supervisors and let it crash is giving you a good design. But that's not enough. You still have to test, of course. You've seen maybe in other courses that testing is important. So Erlang provides a whole spectrum of tools, starting with very simple unit testing, including test generators, so higher order programming for generating tests, and what Erlang calls fixtures. This is if a test needs some input to be set up before and something to be done after to get the information out. So this is this eUnit framework, which supports test-driven development for testing modules and libraries. The next one is called Common Test. This is a system testing framework. With this, you can test the whole system, and you can do important things like testing race conditions and fault injection. If I have a concurrent system, I have what's called test groups. I can run tests in random order and to see whether there are non-determinism issues in the test. I can call test suites to handle independencies, and I can also simulate abnormal termination, fault injection. So if my system is robust, if it survives a crash, I have to test that. So the testing will force processes to crash. It will do fault injection as part of the test. So this is the Common Test full-featured framework. And then there's an interesting tool. There's a couple of very interesting tools in addition to that. One of them is called Dialyzer. Dialyzer is actually a type checker. It does type inference. So remember, we said Erlang is dynamically typed, not statically typed. So you can have kind of type errors sometimes. Well, Dialyzer kind of fixes that in many cases. It actually will find type errors. It will find mistakes in the types. And so it gives you already back some of the advantages of static typing, if you want those advantages. Okay? So that gives you the basic idea now for Erlang. You have the behaviors, the generic behaviors, and the supervisors. You have the stable storage, which is the friend of supervisors. Together, they manage the fault tolerance. And then you have the testing, which is the friend of the design. The design is good, but it has to be tested, of course. But of course, the testing will usually be straightforward. The design is made to be fault tolerant, but you still have to test it because maybe you did a little bit something wrong somewhere. But once you test and you see that it's solid, the design, then the system will be extremely reliable. Okay? So that gives you then the basic principles of building applications in Erlang. What I want to do now is talk about how servers work, and then I'll talk about supervisor tree, which is a very important concept. But let me first go back to the chat. Okay, so you've seen, there's a few questions, but let me first say, so you've seen now the basic principles. So let it crash, which means crashing is good. That's another slogan. Failure is good for process. So if a process has a problem, let it crash, and then you have a supervisor looking on top. You have the stable storage, so the supervisor can restart the process with a new state. And then you have behaviors. So you don't have to write any code for this. It's done already for you. The Erlang OTP supports all of this. So this makes it very easy for the programmer. Let me answer now the questions. So question, what if a supervisor crashes? That's a very good question. So the supervisor is actually looking at these process node. So one way the supervisor itself can have problems. So the supervisor will see there's a problem and will restart. Okay? It sees there's a low-level problem, maybe contention, maybe a conflict, maybe low-level overload, maybe an error in the computation. It restarts. And then the system keeps running, and another time it has to restart. So the supervisor may be restarting the processes many times, but maybe too many times. You see, maybe the same error is always coming back, so the restarting is not solving the problem. In that case, the supervisor itself will fail, and the supervisor will actually have another supervisor which is higher up. So it's a tree. So the supervisors actually manage the behaviors. These are the first level supervisors. They're looking at behaviors, but all these first level supervisors are managed by a second level supervisor, which is looking at the supervisors. So the second level supervisor will see if there is a part of the system having a problem. Maybe it requires some other kind of a fix. Maybe the system is attempting to do too many calls, and we have to do some other fix like reducing the throughput or something. So there's actually a second level supervisor that you can write, observing the first ones. And if you look at AXD301, it actually has a two-level supervisor hierarchy. So it has the supervisors observing the behaviors, and it has a second level supervisor. And actually, I asked Joe Armstrong whether you need more, and he says, no, for the AXD301, two-level supervisor is enough. Okay? When a process crashes during handling a message, this message is re-put in the mailbox or not. So the message comes into the mailbox, and then the process crashes. That message will disappear. Okay? It will not be put in again. And so there will not be, the message comes into the process, and then the process crashes. When it's restarted, the message will not be reappeared. It's gone. Okay? That's why you have to terminate all of the processes in a link set. Because maybe another process send me a message and I crash and I'm restarted, but the other one, there's a problem still because the message has disappeared. So the other one cannot continue either. So that's why you have to restart the whole link set. Okay. Question: is the supervisor and let it crash concept available in other languages? Partly. In other languages, typically you will use fault-tolerant libraries, but the system itself has really no mechanisms, basic mechanisms for handling fault tolerance. So the concept, as far as I can tell, is still very attached to Erlang. And the reason is that Erlang is completely built on message passing, whereas other systems like Java are built on shared state. So they have a different foundation. So you cannot use supervisors on a system built with shared state because you don't have the independence. Okay? So the answer is that the concept is still mostly existing in Erlang, but there are a few message passing systems. There is a system called Akka, which is built on top of Scala, which are incorporating some of the Erlang ideas. But it only works if your system is doing message passing. Okay? Otherwise, for shared state systems like Java, you cannot use supervisor concept because it's designed for message passing systems using independent active objects. Okay? So it's kind of still very specific to Erlang. You see, when Erlang was designed, a lot of people have been working on Erlang. So Erlang has a head start. Other systems are starting to copy now the Erlang ideas and make systems with agents. But Erlang people have not been sitting still. Okay? All the ideas I show you now are still being developed, and new ideas are still being added into Erlang. Okay, let me now show you how the servers work first, and then I'll show you how supervisors work. So supervisors, generic servers, very interesting. And you'll see it's very easy to understand if you understand a little bit higher order how that works. So let me first explain generic servers. Okay, so here let me show you a server. Let me show you a very simple client server, and then I'll show you how to make it generic and specific. So let me show you first a simple server as a single piece of code, and then we divide it up into two pieces, a generic part and a specific part. Okay, so this slide here shows you a simple server. The simple server has it does something very simple. So basically it keeps track of channels. So the idea is the following. The server does the following. It manages a data structure called channel, and it allows you to allocate and free channels. So I have a set of channels, and I can call allocate if I want to use a channel, and I can call free when I don't use it anymore. And internally, there's the system manage this as a data structure. Okay? So the channels are represented by atoms. So I have a set of channels. I allocate, I get one. Okay? So there's an allocate function which returns a channel. And then there's a free. When I want to free the channel, I put it back into the free. So it's basically you have a set of allocated channels and a set of free channels. When I allocate one, I move it from free to allocated. When I free one, I move it back from allocated to free. So I have a simple data structure managed by channels, allocate, and free. So these are the basic functions. And the server turns this into a server. So it receives allocate message and it receives a free message. Okay? So this loop basically implements the server. It can receive these two messages. It does some work here. It calls allocate. It calls free. So I won't show you right away. So channels, allocate, and free, there's actually an implementation of that a few slides farther. So it's actually here on this slide. So, but I include the slide to make the example complete. But for now, you can assume that channels, allocate, and free are functions that exist. Okay, and I want to turn them into a server. So I create a server here. Notice the server, I register it. I call it ch1, channel 1 server, and it will run in a loop, and it will take two kinds of messages, an allocate and a free. And then I have an interface here where I can turn them actually into functions, where the allocate function will send allocate message to the server, and it will receive the allocated channel, and the free message will send the free to the server. Okay? So you see how it works, huh? So the allocate, an allocate will send a message to the server. So here is the server, and it will return the allocated resource, and the free message will send the message to the server, but it doesn't need any reply. Okay? So this whole slide shows you this one application built on top of this channel data structure and allocate and free. You see, it's very straightforward kind of application. Huh? I'm not trying to do something complicated, and it's actually something realistic. Now, so this is a server. Let me now split it into a generic part, which is the actual server loop. So this is the server loop. Huh? And then the specific part, which is this functions. So if I want to write another server, I would have to write this loop, and I would fill in new functions here. So let me write now a generic server. So here's a generic server. Okay, this server will do any kind of thing. And the way it works is that it will do a call, and it will not do allocate, but it will do any kind of a call that receives a message. It will also do a send without returning. So in Erlang, this is called a cast. Cast means throwing something. Huh? So the call does round trip, and the cast does a simple send. And the server loop is here. So it's a loop doing receive. It does recursive call here. And the red code is actually the functions I want to do. So there's an init function, there's a handle call, and handle cast. So this is a generic server. And the way to make it specific is to fill in the blanks, is to define init, define handle call, and define handle cast. And then it turns into specific server. Okay? But this generic server code on this slide will let me build any kind of server. Of course, this is a simple one. Huh? This one is not doing fault tolerance. Okay? It's not doing things like start and stop and registration automatically. And it's not doing a lot of things, logging. It's just doing the basic server. So the real gen server is doing a little bit more. But you can see this is the basic idea. This is a generic server. And now to make it specific, I have to fill in these three red functions. So here's the filling in. This is called the callback module. So to make it specific, I have to define a callback module. This is the only thing the programmer needs to write. So the generic server is already in the system. So here in the red box is the connection between these generic things and the actual calls I need to do. So init, handle call, handle cast, I have to define them. So init is calling channels, handle call of alloc is calling alloc, handle cast of free is calling free. Okay? So this is the connection between the generic part and the specific part. And then I can do other things. I can define the alloc and free if I want to turn them into actual kind of, to make them look like procedure calls, I can do that. But the basic connection is done in this red box. Okay, so you see how it works? I have a generic server here, generic server loop, and the filling in the blank is the red part, and then I just have to write the callback module. So the programmer only has to write the callback module. Okay? So here's the channel implementation. I won't go into so much detail. So channels are managed as a tuple of two things, a list of allocated channel and a list of free channels. Alloc will take a free one and put it in the allocated list, and free will take an allocated one and put it back in the free list. These are the functions I'm using in the previous example. So I won't go into detail here. You can look at it if you want. It makes the example complete. Okay? The channels, this is the functionality. It could be anything. This is how I'm using it in this example. Okay, so the full gen server provided by OTP is extending this example. Okay, this example shows you the basic server. And what can you do? So the basic server lets you start, and you need to have a callback module. And then you have two kinds of server requests. Synchronous request, which goes round trip, and asynchronous, which is only going one direction. So in Erlang, this is called call and cast. Now, the cast is the asynchronous, call is synchronous. And then, of course, I can stop it. What I did not show is that the real gen server can be part of a supervision tree. The server will automatically be terminated then by the supervisor. It can also be restarted if there are problems. So I won't explain the details of that. I can just say that the server, the gen server, can actually be part of a supervisor tree. Okay, so that's the gen server example. So I will go back to the chat now, and then I will explain supervisor trees. So the basic idea of the gen server and how they're managed using supervisor. So let me go back now to the. So you see how the generic server works. So I've shown you the example in Erlang code, but it's actually kind of higher order example. I have a template, and I just have to plug in the higher order functions that I need to make it specific. So it's not really very miraculous. It's very straightforward in a language that supports the higher orderness. So you can see how it works for the server. But the real gen server is doing a lot more work for you. The real gen server is living inside of a supervisor hierarchy. Okay, so you see how the gen server works? Let me now show you the supervisors, the famous supervisor concept that I have already been so much talking about. Now I will show it for you, give you more information on how supervisor works. Supervisor trees. So what is the principle? So we want to build fault-tolerant systems. It turns out most faults and errors are transient. For example, a message is dropped on the network for some reason. That's transient because if you try again, maybe the message will go through. Or there's some kind of timing problem. Part of the system times out. It's congestion, for example. Or startup problem. The system is starting up concurrently. Because of timing issues, it starts up in the wrong order, and there's a problem. Maybe there's a deadlock. Deadlock is a timing problem. So timing problem, for example, deadlock is a timing problem. If you restart and execute again, the deadlock will probably not occur. Remember we talked about deadlock. It actually depends on precise timing. So the supervisor tree will actually fix deadlocks. So the way it works is the basic strategy is simple retry. It's very naive, actually. The basic strategy of a supervisor is to restart the problem and to let it run again. So the supervisor tree is favoring retrying. It's not the only thing it does, but the first thing it does is simple retry. So a set of processes are supervised. That means there is a process observing them and seeing whether they're running normally or failing. Okay? The supervisors have authority over the supervised process. They can stop them, they can cause them to terminate, and they can restart them. Okay? And supervisors can themselves be observed in some cases, as I mentioned in the question. And the supervisor tree themselves is carefully implemented, so there's no internal problems like race condition and so on. So the starting of a supervisor tree will be synchronous. So this is already implemented. The programmer does not have to worry about this. The supervisor tree itself is very carefully implemented. So that's the basic principle. So a supervisor tree is a hierarchy. So it has a root. It's kind of like a tree. It has a set of supervisor nodes. So here's some supervisor nodes. And then there's some worker nodes underneath, which are supervised. Okay? So a supervisor node can start, stop, and monitor its child processes. And all the Erlang behaviors that we saw, that I mentioned, server, event, and FSM, are working with supervisors. So there's the basic restart principles. First of all, there's the restart strategy, and then the restart frequency. So the restart strategy is, the two important ones are one for one and one for all. There's also a third one called rest for one. So I'll explain a little bit how they work. So one for one means if all the processes are doing independent work, if one of them fails, you just restart it. One for all means they're actually working together. It's like they're all linked. If one of them fails, they all have to be restarted. Okay? And rest for one means that there's some kind of a chain. If one of them fails, some of them have to be restarted, but not all. So the restart frequency, so this is depending how often you restart. So if I'm restarting, but then the problem occurs again, and I have to restart again. And then the problem occurs, and even again, and I have to restart again. If this happens too often, if a process dies repeatedly for the same reason, then the supervisor strategy is not working, and the supervisor itself will terminate. So this actually is very effective. Most errors are fixed by restarting, but not all of them. The ones that are more complicated are fixed at a higher level. Okay? So in the AXD301, there's actually one higher level that does this. Okay? So here's an example of a hierarchy. So the circles are the workers. Okay? These are worker processes. And you can have more of them even if you want. And you have two kinds of supervisor here, the one for all and the one for one. So the one for one will, if one of these has a problem, it will only restart one of them. Whereas the one for all, say this is a one for all one, it will, if this one breaks, it will restart all of them. It would force them all to fail and it will restart completely. Okay? So basically it works like this. So the two main forms of supervision are one for one and one for all. And one for one, for example, happen when you manage telephone circuits. If I have a bunch of independent circuits, each managed by a single process or by a subtree, if one of the circuits has a problem and has to be restarted, the others are independent, so they don't have to be restarted. So that's one for one. I only restart the failed process. But that's not enough. Sometimes I need to do more, and there we have one for all. So assume we have an application doing things. We have database here, we have a computation task here, we have user interface, we have networking layer. They're all working together. Assume now one of them crashes. Then we have to restart all of them because they're actually dependent on each other. And if you stop one, the others cannot continue. So Erlang let it crash says we force them all to crash and we restart them in a consistent state. Okay, so that's one for all. So those are the two basic supervision strategies. Okay, you see that? See how it works? It's rather straightforward. It works because of the Erlang share nothing philosophy. You see, this approach works because the whole system is built on independent processes. Okay, let me go back to the chat. So you see that? Any questions on that? So you see, supervisor concept is very important, and it's connected to the behaviors. So all the behaviors are taking advantage of it. And you can see that the FSM behavior, you have seen that. We've seen it in the course. The lift control system is exactly using this behavior. So with Erlang, you could build a completely fault-tolerant and robust lift control system very easily. It would be able to control your whole lift even if you have parts of the system crashing all over the place. They would still work. You see? So the lift control system, we gave you an application code using port objects, but it's not fault tolerant, okay? Whereas the Erlang one would automatically be fault tolerant with very little effort from the programmer. Most of the hard work is already done inside of the Erlang. So you see how that works? So let me give you a very brief explanation now of the other generic behaviors. I'm not going to say so much because this is just one lecture and we've seen the generic server. So a very important one is the generic finite state machine. So this one you understand well because we saw the lift control system. So this one is exactly doing that. You have this function going from states and events to actions and state. This is exactly the state diagrams we saw. If we saw in a state S, an event E occurs, so this is a state S going to S prime. So we have an event occurs and we have actions. So this is what we saw in our state diagrams, exactly. And this Gen FSM lets you do many things. It handles all the notifications, you managing the actions, starting, stopping, and it can be part of a supervision tree. Okay, so that's Gen FSM. There's also generic event handlers. This is similar to the tuple spaces. An event is a message that's sent when some condition happens. So when there's an error, you can have an event, an alarm event, something's going wrong, or information has to be logged, it has to be stored on stable storage. The database, when it's doing things, maybe you want to collect this information to store it. So the event manager manages the event handlers, okay, and the notifications. And again, it all lives inside the supervision tree environment. So you see, all these behaviors are part of the supervision trees. Okay, so now let me conclude now. So we have seen in this lecture a very quick summary of the basic concepts of Erlang and of the philosophy and the behaviors concept, and especially the supervision tree and the generic behaviors that Erlang uses to build fault-tolerant and long-lived applications. Okay, so Erlang OTP provides you a huge amount of library support for this. You can get it, and you can see it's actually very easy to use. So the Erlang languages gives you the basic principles. Active agents that share no state and that send asynchronous messages, and the processes are pure functions. They support dynamic code update and failure detection through linking. And then on top of that, we have behaviors, supervisor trees, the testing, also the stable storage. I should mention it here. And that gives you a full-fledged package that makes it very easy to build very robust, long-lived application. And it's used in many industrial applications. Actually, there is a talk. There is, maybe you have played the game Call of Duty Black Ops or other games. Black Ops. This game is actually built on top of an Erlang infrastructure because it's a worldwide game with many users that has to be extremely reliable. So there's actually, I have actually some slides on that I can send, but it's an example of an industrial application using Erlang. I can mention Elixir, which provides Java-like syntax that has Erlang semantics, and both Erlang and Elixir are supported by the Erlang Ecosystem Foundation.